Okay, in this video, we're going to be looking at starting to solve these first order recurrence relations we've been looking at. This is going to be focused on giving you some intuition to why the method works. There's going to be a following video which really just gets into the step-by-step process, but this should give you some understanding rather than just blindly going through those steps. So we're going to start with a fairly simple first order recurrence relation. When I'm saying first order, I mean that each term only depends on the previous term rather than, as we may get onto with second order recurrence relations, where it depends on the previous two terms. So that's what I mean by that language there. So as I say, we're going to be starting with a simple example here. I'm going to give you the example n plus 1 is equal to 3 un. About as easy as we can get here. You should probably be spotting straight away this is a geometric sequence because each time we're taking the previous term, we're multiplying by 3. So I haven't yet given you the first term or indeed any term in the sequence, which means you're not going to be able to give me a fixed nth term, but we may be able to give a general solution to describe what sort of sequences may satisfy this. So can we come up with any ordinal definitions, any position to term definitions that would satisfy this recurrence relation? Well, a simple one would be, so one possible would be if we had un was just equal to 3 to the power n. Hopefully you can see that would satisfy it. If the nth term is just 3 to the power n, then definitely we're multiplying by 3 each time and that would satisfy it. But it's not the only thing that could work. We could have un is equal to 2 times 3 to the n. That sequence would go 6, 18, 54, and so on, and we're still multiplying by 3 each time. That number could be anything, really. We could go for kind of 17 times 3 to the n, or I could put a horrible number there. I could go on listing forever. You might be thinking, if you're thinking about geometric sequences and you're thinking, well, hang on, the nth term of a geometric sequence is a times r to the n minus 1. You might be saying, well, if our first term's 2, maybe we could write it as 2 times 3 to the n minus 1. I'm not really considering that as that difference because this is the same as 2/3 times 3 to the n, so we can still get it in this form. So what I want to say here is that a general solution to this, and this is proper vocab that you need to know now, if you're asked for a general solution, is saying without worrying about any initial conditions such as u1 or u2 or u0. So a general solution here, hopefully spotting from what we've got here, is going to be some number times by 3 to the n. And yeah, we could write as some number times 3 to the n minus 1, but this is going to be a nicer form for us here, so we'll stick with that. Now, at this point, we can verify to check it works. If you're in any doubt here, let's do a quick verify. And this is things you might be asked to do on the papers given an nth term, and that's to verify. All this means is we're going to sub in to both sides of this and check that we get the same thing on both sides. So our left-hand side there, if we substitute in, is just un plus 1. Well, un plus 1, in this case, would be p times 3 to the n plus 1. And the right-hand side of our recurrence relation was 3un. That's 3p times 3 to the n. And if we use power laws, that's just p times 3 to the... Sorry, my pen going dodgy again. Times 3 to the n plus 1. So we've got left-hand side equals right-hand side, and we've verified that it does indeed satisfy it. Okay, so that's a general solution. What if we're given an initial condition? So let's say I might now tell you that u0 is equal to 5. We will sometimes be given u0. Sometimes we'll think about sequences starting at u1. Sometimes we'll think of u0. As long as we're consistent with the notation we've got, we should be fine. So if u0 equals 5, then subbing in to that general solution we've got of un equals p times 3 to the n, and replacing n with 0, we're going to get u0, which is 5, is equal to p times 3 to the 0, and we'll just get that p is equal to 5. And this tells us that in this case, with this initial condition, we're going to get a un is equal to 5 times 3 to the n. Our language for describing this specific thing is this is the particular solution because it's particular to that initial condition. we could, if we got given a different initial condition, we wouldn't have to work through the question from scratch. Our general solution would still be the same, but our particular solution, that constant, would have changed there. Okay, so far so good. It looks like we're just working with geometric sequences because we were just given something where the next term depended on the previous term with nothing else involved there. So I want to start to complicate matters a little bit now. So in the next example we're going to look at, I want to tell you that un plus 1 is equal to 5un, looking similar so far, but plus 12. Now, this definitely isn't going to be a geometric sequence now because we're not just multiplying by 5 each time. Yes, we're multiplying by 5, but then we're adding 12, and that's going to completely change things here. So this is definitely more complicated. The language we have for this is that it's a non-homogeneous recurrence relation. That's saying, so it's homogeneous if we just have terms of un plus 1s, uns, or even un plus 2s. If we've got anything else added on, whether it's a constant or whether it's something more complicated, as you will see in future, that is then when it becomes non-homogeneous, and that's where it gets more complicated. So, first idea, can we find any solutions to this recurrence relation? That's our first challenge here. Well, let's go for it. So we're just trying to find anything that works. It won't necessarily be general in a moment. And my question here is going to be, given we've added a constant, is there a chance that there's any constant that just works? So un equals a constant. So that's what I want to try here. So we're going to try un is equal to some constant. I'm just going to call it a here. This is what I'm going to call my trial function because I'm hoping I can get something that works. If we do this, then let's sub in. So un plus 1 would still be equal to a. So when we sub in, we're just going to get a on the left-hand side. 5 times un is 5a plus 12. Well, this is nice and easy to solve. We can rearrange. I'm just going to jump through. And we'll get that a is equal to negative 3. So un is equal to negative 3 works. But if I gave you an initial condition here, if I told you u0 equals 6, this isn't very general and we wouldn't be able to solve it. So it works, but it's not the most general possible solution to this recurrence relation. And we're now going to have to go more broad. So in order to go more broad here, our next idea is to say, well, let's simplify this momentarily. Let's go back to, we saw that if we had un plus 1 equals 5un, if we just had a homogeneous recurrence relation like this was nice and easy because it was a geometric sequence. So let's think about solving this first, and then let's see if we can combine these two ideas together. So if we solve this, it's a recurrence relation. Sorry, it's a geometric sequence with a common ratio of 5. So the general solution for that would have just been un is some constant times 5 to the n. As we've said, we could put 5 to the n minus 1, but it's just making our lives a bit harder, so we don't have to. It would just be a different value of p on the same initial condition. So we've got this, but remember, we're trying to solve. So the recurrence relation we're given, the recurrence relation we're really after trying to solve, I'm going to rewrite it just a little bit, is un plus 1 subtract 5un equals 12. Now we've got two useful pieces of information at this stage. We've got one thing. We've got our this thing, which I'm going to call our complementary function. The thing that solves the homogeneous equation, once we've simplified it, is our complementary function. I'm normally just going to call that write CF. I'm not normally going to write it out fully every time. So we've got our complementary function, and that is un equals p times 5 to the n, and we know that solves un plus 1 minus 5un. Sorry, my pen is just playing up. Minus 5un equals 0. We know we've got our solution. We also have our trial function, which was un equals -3. That's the one we tried earlier and found it worked. And what did we find out? We found that solves un plus 1 minus 5un is equal to 12. Now, can we find some way of combining this? The idea is, if we add these together, if we combine our complementary function and our child function by adding them together, we're actually still going to solve this recurrence relation we're after, which may not sound obvious, so let's go through it. So what we're saying is, so if we say un is equal to p times 5 to the n, our complementary function, the thing that satisfies our homogeneous recurrence relation, subtract 3, that's adding the child function that we know works, then when we do un plus 1 subtract 5un, what we end up with is, well, un plus 1 is p times 5 to the n plus 1 minus 3, and then subtract 5 lots of p times 5 to the n minus 3. If you simplify here, you're going to get p times 5 to the n plus 1 subtract 5p times 5 to the n. These things are the same, so those things are going to simplify, and you're going to be left with subtract 3 plus 15 by doing your -5 times -3, and you're going to end up with 12. So this un is p times 5 to the n subtract 3 solves the recurrence relation we were trying to solve, and it's the combination of the two, and this is what we're going to say our general solution is. So our general solution is, and this is always the case, is going to be our complementary function, the thing that satisfies our initial condition, plus our child function, anything that we found that solved the overall complicated thing. And in this case, what that's given us is p times 5 to the n subtract 3. And that's our general solution. Now, what if we're given an initial condition here? Let's just think about that. This is nice and easy compared to the rest. So I mentioned this earlier. Let's say if u0 was equal to 6, before we wouldn't have been able to deal with this at all. We'd have been stuck because we just had un equals -3. Now, though, we can just whack it into both sides. So we're going to get 6. Replacing them with 0 on the right-hand side is p times 5 to the 0, which is just p. Subtract 3. Sorry, that's a 3 there. And we end up with p equals 9. And our particular solution, that's the one that satisfies this initial condition, is un equals 9 times 5 to the n minus 3. In the next video, I'll just do 1 or 2 more examples like that, but without all the explanation going along, just going through those steps, because ultimately you do just want to be able to replicate those, but the complications will come as we have to do more and more complicated child functions if you have a more complicated function added on to your right-hand side. Thank you very much.